All right, ladies and gentlemen, this is going to be the last portion of the notes for this week, how to draw ionic solids in crystal lattice structure, followed by how to draw particulate level diagrams for metal alloys. Before we get into how to draw anything though, I just want to review really quickly what an ionic solid is in the first place and how ionic solids form. So if we look at this picture, what you're seeing here is a sodium atom over on the left-hand side here and a chlorine atom. Now, when those two things interact with one another, we have to remember that sodium does not have a very strong electronegativity. So we call this thing electropositive overall. Chlorine, on the other hand, has a pretty strong electronegativity value. And so sodium's outermost electron floating out in its outermost shell is literally just going to cruise its way over to chlorine because chlorine is going to yank that electron away from sodium. What you get as a result from that is the sodium ion, Na+, and the chlorine ion, Cl-. Those two ions have opposite charges, and as such, they are then attracted to one another. And it is that attraction that creates the ionic bond. It's not the electron transfer itself that is the bond, it is the attraction between the resulting ions. So as you can imagine, if a lot of those ions are around each other and stack up next to one another, you get a structure like this, and we call this a crystal lattice, because positive and negative ions are just going to stack, alternate, and form a giant crystal of those alternating ions. So in a way, ionic bonds are really, really special in that one ion can ionically bond with a bunch of ions around it. And you're seeing that happen here because this one sodium ion pictured in the corner is ionically bonded with this and this one and this one. This one in the middle is ionically bonded with 1, 2, 3, 4, there's one behind it. So 5, up to 6 potential ionic bonds depending on where that ion is in the crystalline structure. All right, so that is what a crystal lattice structure is. In terms of how you should draw them, there's a couple of things you should pay attention to. The first is size. Size is super important, especially on the AP test, because they on the AP test are going to be looking for you to understand how big are those ions. So ionic radius is what you're paying attention to. In addition to ionic radius, the size of your particle, you want to make sure your particles are oriented around each other correctly. Basically, are the charges correct? For example, sodium has a positive 1 charge, chlorine has a negative 1 charge, magnesium has a positive 2 charge. You want to represent these things in your diagrams. But more than that, you also want to make sure that you are alternating charges, right? You want to have positive, negative, positive, negative, positive, negative. We don't want two positives to be next to one another. We don't want two negatives to be next to one another because, as we recall, like charges repel and opposite charges attract. All right, so let's look at a couple of practice problems here. Practice problem number 1 says a student incorrectly draws the following particulate model of lithium bromide, LiBr(S). And if you recall, this S here means solid. Explain the student's errors in the drawing. So let's take a look at that drawing. Over here, we see that they have right off the bat, all their positive charges are together. So immediately, they are not alternating charges. So let's make a note of that. And going back to the photo, we can see that they're doing the exact same thing with the bromines. So while they have alternated charges this way, they have not alternated charges going that way. So that's incorrect. The next thing that they did that's an issue has to do with the ionic size. So if you take a look at your periodic table, lithium is a very, very small atom. right? Lithium only has 3 electrons, which it loses one of when it ionizes. So lithium should be small. Bromine, on the other hand, is much, much, much bigger. It has way more shells than lithium should have, so this one should be large. Now, when we talk about that, you are going to say that the student incorrectly represented ionic size. But you're not just going to say incorrectly represented ionic size, you're going to describe how they screwed that up. And you're going to say lithium should be smaller than bromine. All right, this particular practice problem does not ask us to redraw the particulate level diagram correctly, but something on the AP test might ask you to do that, in which case you would literally just redraw it more accurately. Practice problem 2 says draw an appropriate particulate level diagram of potassium chloride, or KCl. So real quick, I'm going to just pick 2 colors to assign to our KCl, just so we don't get confused. Potassium is in group 1 on the periodic table, so that one is going to be K+. Chlorine is in group 17 on the periodic table, so that one is going to be Cl-. Now, if we look at the size of both of these ions on the periodic table, we find that potassium is in group 4, but it's going to lose that outermost shell when it ionizes because it loses that single electron. Chlorine is in period 3 on the periodic table, meaning it has 3 shells and it's going to gain an electron when it's ionizing. And so realistically speaking, both of these ions are similarly sized. K+ and Cl- are similar. So when we draw it, they should in fact be similarly sized, all right? And remember, we want to pay attention to not only size, but our charge alternation. So when you draw this out, I generally like to make a 3x3 grid of my ions when I draw out particulate level diagrams. So I'm just going to make that. And again, we're going to use similarly sized dots because those 2 ions are of similar sizes. All right, so taking a look at what I've done here, I see that my charges are positive, negative, positive, positive, negative, positive. So I've alternated my charge in both directions, and I have represented both of my ions sized correctly. You do not have to pay attention to those little minute size differences when you are drawing a particulate level diagram, because on the AP test, you're not going to have access to very specific size information for a question like this. We know that our potassium ion is just a hair smaller than our chlorine ion because it has 2 more protons than chlorine does. But that size difference between these 2 ions is actually very minuscule. So we're representing them as the same size, and that's perfectly fine. All right. So in terms of metals and metallic bonding, once again, I just want to pause for a second and review what a metallic bond is. All right. So metallic bonds are different than anything you've studied so far because metallic bonds generally take place between 2 metals. Okay. And as such, Metals generally are pretty electropositive, and what that means is they don't have a strong pull on their electrons. So if you look at a representation of a metallically bonded substance like the ones over here, you see that the electrons are kind of in random spots all over the place. And that's because none of those metallic nuclei are going to want to hold on to them. Those electrons can just cruise wherever they want to in that metallic substance. And as a reminder, that's what gives metals all their really fun properties like electrical conductivity and heat conductivity and malleability and ductility. It's that movement of electrons, the ability of them to cruise around. So typically, when you see a metallic bond, it's going to be represented something like this, with just a shaded region around a bunch of positive nuclei. And that shaded region literally is meant to represent the electrons themselves, because they can move all over the place, and so we just shade in that area to represent all the places they could be in a metallic sample at any given time. All right, alloys generally occur between two or more metal elements. So again, usually between metals. However, sometimes alloys can exist between metal elements with nonmetals trapped in between them. So carbon, for example, is an essential component of steel along with metallic iron. There can be nitrogen or silicon or something else that just kind of gets trapped in that overall alloy structure. So if we take a look at the picture over on the right here, it compares different types of metallic samples that you might see. So up here on the left-hand side, we have a sample of pure metal. You can see that it's pure. All the dots look exactly the same. They all represent atoms of the same metal element. But if you look over here on the upper right-hand side, we see what's called a substitutional alloy, which basically means that atoms of a different metal element, like these blue dots that you're seeing here, have substituted in for some of that original metal atoms. On the bottom left here, you're seeing what's called an interstitial alloy. So it almost looks exactly the same as the pure metal sample up there, but these little tiny dots, little tiny either metal or non-metal atoms have just squeezed into the empty spaces between the original metals atoms. And then finally, over on the bottom right over here, you're seeing kind of a combination of all of them, right? You're seeing a substitutional / interstitial alloy, which has multiple different metal atoms in it. We see some of the original red ones, we see some of the blue ones subbing out in place of some of the red ones, and we see those little green dots have squeezed into that empty space in the middle of all of those metal atoms. All right, so in terms of how you would represent particulate level diagrams for alloys, you're paying attention to largely the same thing you've been paying attention to for crystal lattice structures. You want to make sure that your size of your particles, or again, your ionic radius, is correct. And you want to make sure that they are oriented correctly around each other. So if you have, say, a large and a small, then you should probably be drawing an interstitial. However, if you have two metals that are both around the same size, so if you have two large ones or two small ones, you're probably going to want to draw a substitutional alloy. All right, so let's look at this practice problem here. This practice problem says draw an appropriate particulate level diagram to represent the alloy bronze, which is a substitutional alloy composed roughly of 70% copper and 30% tin. All right? So, paying attention to copper and tin on the periodic table, copper is Cu and tin is going to be Sn. We figure out, if we look at their positioning on the periodic table, that tin is in the row below copper, and so tin is just going to be a little bit larger. Not a ton, but just a little bit. Okay? So once again, I'm going to make a 3x3 grid, or you could choose to even make a 3x4 grid of these copper and tin atoms, keeping in mind that the problem tells us that copper should be most of this thing. All right, so that one's going to be copper, that one's going to be copper, that one's going to be copper. Then we're going to make just a slightly bigger tin. Copper, copper, throw another tin down here. All right, so we have made my 3x3 grid, and I've included a total of 7 coppers and 2 tins, which isn't a perfect 70%, 30% split, but it's close, because to do 70-30, we would have had to have 10 atoms overall, and my grid only had room for 9. But this is totally fine. You have represented your size of your particles, so the tin ones were just a little bit larger than the coppers. You have approximately the correct percent difference between your copper and your tin atoms, and they are oriented correctly. In this case, it does not ask us to represent the electrons at all. If it had, we would have just done a little bit of shading around this diagram to represent those electrons and how they can cruise anywhere, anywhere, anywhere within this substance. And I know my shading is a bit crude, but you'll have to forgive me for that, as I am doing this on an iPad. But either way, that is a perfectly acceptable particulate level diagram for a metallic alloy like this. If you have any questions about how to draw alloys, how to represent them, how you know it should be substitutional versus interstitial, please don't hesitate to ask.